Hello, everyone, and thank you for joining us. My name is Tom Herron, and I'm involved with market transformation and education at NFRC. As part of this initiative, we bring you our Emerging Technology and Sustainability webinar series. And this is where we discuss the latest thinking in fenestration and green building, along with insights on market trends. Today's webinar is entitled High Performance Fenestration for Net Zero Building, an Innovation or Deployment Problem. Our speaker is Helen Sanders, who has over 25 years of experience in the glass industry and in architectural coatings and dynamic glazing. Helen is a general manager at Technoform North America, a member of several fenestration industry organizations, and also an NFRC board member. Helen also holds a PhD in surface science from the University of Cambridge, England. And with that, I'm confident we all have a lot to learn, so I will hand it over to Helen.
Well, good afternoon, and thanks for the introduction. At Technoform, I like to say that we don't make windows, we make windows better. And the question that I hope to address in this webinar is whether we have an innovation problem or a deployment problem to achieving the fenestration performance that we need to get to net zero buildings. And that's the question I'm going to be exploring through the presentation. So in terms of an outline, I'm going to start by talking about what's net zero fenestration, what's the definition, and then look at some of the current technologies and the state of adoption, with a look to the globe for a fuller comparison. And then I'm going to take a look at the impact of energy codes and then some other systemic barriers. And then we'll close up with some case studies that really show how a deployment can be driven. So what does net zero fenestration look like? So the US Department of Energy defines a net zero energy window as one with better than R5 thermal performance. Now, in some climates, it will be even better than that. And in other climates, it won't be quite as low as that, and it will also so it'll really depend on climate, the U factor, but on average, it's about an R5 thermal performance, which is a U factor of 0.20 in IP units. In addition to thermal performance, you need dynamic solar control, and that can be achieved either through mechanical shading or through dynamic glazing, such as electrochromic glass. And then in combination with that, we need to harvest the daylight and energy through dimmable lighting controls and also photovoltaics, where that happens to be integrated into the fenestration through the visible portions or on the opaque areas. So that's DOE's net zero window. So as you see here, the low U factor fenestration with wide thermal barriers, plus the dynamic solar control, plus integrated, what we call integrated facades, which is the integrated with daylight and energy harvesting. So the current building stock, when you think about it, the cost of energy due to windows, the DOE estimates at about $2 billion annually. If you implemented net zero windows throughout the current building stock, you would save 15 billion annually, and actually you'd have a net surplus of energy. Again, that's because of the harvesting, the daylight harvesting and the energy harvesting. We actually have the technology to get to net zero fenestration today. So let's look at the innovation in fenestration. You know, where do we stand? So let's start by looking at the, starting with the glass and dynamic solar heat gain control. So we have dynamic glazing technology. It's 20 years old. It's been at least 20 years since the first electrochromic glazing was installed in North America. It's available from several manufacturers. Mechanical shading, that's got an even longer track record. There's double skin curtain wall. Double skin curtain wall is ubiquitous around the globe, with several manufacturers. Now let's go to the thermal performance. So triple pane insulating glass. Again, that's been around for way more than 20 years. Again, you can get it from many manufacturers. It gets you to an R8 center of glass performance. Again, the center of glass, not the whole assembly. There's a vast selection of low E and solid coatings, single silver, double silver, triple silver, and now even quad silver coatings. Those technologies have been available or around for over 30 years. And available from many manufacturers. Over the last 10 years, room side low E coatings have become available. There are several products from several manufacturers available. Typically, it goes into, they're used in double pane insulating glass unit on the room side to allow you to have two low E coatings that can give you a center of glass R value of about 5. If you want to go further, you can look to vacuum insulating glazing. Again, that's got a pretty, everyone thinks about this as a relatively new technology, but it's actually not. It's been available the technology has been available for 20 years. And again, several manufacturers are actively selling this product. Gives you an R14 to above R16 center of glass. What I'm showing here is courtesy of Vitro architectural glass. On the left is the regular monolithic vacuum insulating glazing. On the right is the combination of a vacuum insulating glass unit with another pane of glass in what we call a hybrid insulating glass unit. So it looks like an insulating glass unit, but the room side pane is the VIG unit. Note here, I've talked about the R value of the center of glass. We know that center of glass is always better than the whole fenestration U value or R value. We really need to address the thermal losses at the system edges to achieve the overall system performance to get to R5 or better. So let's look at the edge, the current available edge technology. So starting with the edge of glass, we have what we refer to as warm edge spacer. Warm edge spacer is spacer that reduces the conduction of heat between the inside and the outside of the building. Typically, they are either a combination of stainless steel and non-metal plastic or non-metal materials. These technologies have been available, many technologies have been available for 20 years. They are available from several suppliers. Typically, again, they are to address one of the weakest links thermally in the window system. There's, as I said, many available with long track records. When we look at aluminum frames, it's key to create a thermal barrier between the inside and outside to prevent conduction there. If you don't do that, you'll have a superhighway of heat going from inside to outside and vice versa. So complex polyamide thermal barriers have been used for 45 years and have developed in complexity and performance during that time. I'm going to dive into that topic in a moment to provide an example of innovation adoption rates. But not forgetting the opaque elements, thermally broken cladding attachments are available to significantly reduce thermal bridging at the edge of panels where they're attached to the structure. This can improve performance by over 50%. So you can imagine how much thermal degradation there is if you attach panels the way we typically do, which is using long aluminum Z-girts. So combinations of these really well-proven technologies can achieve greater than R5 in the fenestration assembly, which is less than 0.2 in U factor in IP units. So here's an example of a North American aluminum architectural window using polyamide thermal barrier technology, triple pane insulating glass, and warm edge spacer. It gives performance significantly better than R5, and it's not a one-off product. There are architectural windows, R5 architectural windows are available from several manufacturers. They have them in their portfolios. In this case, there's a 45 millimeter wide polyamide thermal barrier with foam cavity fillers, which, and again, this technology has been available for at least 5 years in North America and longer in Europe. So as I mentioned, this technology, R5 windows available, again, in architectural windows, available from many fabricators in their portfolios, just not used very often. So this is, I want to use the polyamide thermal barrier technology as an example of innovation adoption in the US relative to other countries. So this graphic shows the evolution of this technology, which was first brought to market in the mid-1970s. So since starting with small barriers around 10 millimeters in width, the widths have grown to as an order of magnitude up to about 100 millimeters wide today. And the wider the barrier, the lower the conduction across the two aluminum extrusions. And along with the growth in barrier width, so has the complexity of the shapes developed too. You can see the addition of legs and foam inside the cavities to reduce heat transfer by convection. And more recently, low emissivity foils have been introduced to reduce radiation, which is the last and smallest of the heat transfer mechanisms at through the frame. And one of the latest innovations in the reduction of conductivity across the edge of the frame is actually in the conductivity of the polyamide strip itself. The technology is sometimes called low lambda. And that means that for any given barrier size, you can get a lower overall U factor if you swap regular polyamide for this low lambda polyamide. In addition, there have been lots of application-specific innovation to allow polyamide thermal barrier technology to be applied to a much wider range of applications, including polyamide pressure plates for curtain wall, anti-bimetal systems for large windows and doors. So this shaded area represents currently the business as usual technology used in Western and Northern Europe. And with the latest developments are used when higher performance is desired. Now in Canada has adopted some more complex shapes, but it's still somewhat behind Northern Europe. However, the US is currently typically using technology dating back to the 1970s and 80s, relatively small thermal barrier widths and really pretty low complexity. Again, this is business as usual as what's installed in buildings today. That's not to say, as I mentioned before, more complex, wider thermal barriers are available and designed into windows. They're just not typically used in our buildings as business as usual. So moving to the edge of glass. So warm edge spacers are an easy way to improve the thermal performance. They can reduce the overall assembly U factors by anywhere from 0.02 to 0.05 in IP units. The highest end of this range I just quoted can be achieved in structurally glazed curtain wall, where the only conduction path, or the major conduction path, is driven at the edge of glass because there's no external emulsion. So what I've shown here is a plastic hybrid stainless steel box spacer, which is a track record of over 20 years and available from many fabricators in North America. But today, we also have multiple types of warm edge spacer in the market from many other suppliers. While warm edge spacer is ubiquitous in Europe, in US commercial construction, the adoption rate is much lower, maybe as low as 20%. So there's a great opportunity for replacing the regular aluminum with warm edge spacer. Again, this is a really easy and low cost solution. It just isn't widely adopted. So as an example, here's a typical window installed in German buildings today. Triple pane is standard. In fact, they charge more for dual pane units because it's a special order now. Warm edge spacer is also standard, along with wide thermal barriers with strategies to reduce convection like foam filling. I'm quoting some European U factors here, as you see in the text. The assembly U factor here is 1.1 watts per meter squared Kelvin, which is just under 0.2 in IP units. But I'm quoting European U factors here, which, as you all know, are calculated differently to NFRC 100 values. The numbers derived from both standards, the European and NFRC 100, tend to be different, but they're not different by more than 10 to 20%. So you can get a sense of the order of magnitude here. So the available fenestration technologies have long track records. They're not new. They're available from multiple suppliers in a combination that can achieve net zero performance. However, this is business as usual in the US. They have a typical fenestration has a small thermal barrier, typically less than 15 millimeters. They use aluminum spacer, and they use a dual pane IGU with probably just one low E solar control coating. That's what we use today. So, you know, why is higher performance not business as usual? So let's take a dive here into some of the reasons why. So one big reason is codes. High performance strategies for fenestration are really not needed to meet US model codes in most climate zones. So the US, so what you see here is the current, the newest model codes and the U factor requirements in climate zones 4 through 8. I've highlighted climate zones 4 through 6, which is obviously where a lot of construction happens, where our big major cities are located that are U factor driven. So well, you can see the U factors required by these most recent model codes are far from the 0.2 or less that we said was required for a net zero window. And these numbers can be achieved without complex thermal barrier systems. And because of the ability to trade off envelope performance with better internal systems in the performance compliance path, often fenestration with even worse performance can be used. So the details to the left here are of a typical curtain wall and aluminum window system. With low E dual pane insulating glass with a warm edge spacer, they can achieve code maximum U factors with relatively small thermal barriers. As you can see here, we're talking about thermal barriers less than 12 millimeters. One thing I do want to point out, though, is that if we look at this window detail, it's actually the same window as the R5 window that I showed a few slides ago. It has the same extrusions, but with a few subtle changes in the thermal break technology. Same extrusions, but instead of the 12 millimeter thermal, simple thermal, dual thermal barriers, they're replaced with the 44 millimeter foam filled barriers. So a very simple change can get you a very big change in U factor. So you can go to R5 with relative ease without changing your aluminum extrusions. So this is an innovative design from this manufacturer, which achieves achieving the thermal performance and aesthetically pleasing sight lines that we're used to in North America, as well as getting getting the efficiencies of production where you don't have to change extrusions every time you want to change thermal performance. And it really demonstrates that getting to R5 doesn't actually have to be difficult. Now, we talked about model codes, but then the model codes aren't necessarily adopted across the country. Adoption of the model codes by states is typically pretty slow, as you can see from this graph, which shows you the current performance of the state adopted codes across the US. Just 10 states and DC have adopted the 2019 version of ASHRAE 90.1, and the 2022 version is already published, and the 2025 version is already in development. And note that 90.1 has a cost effectiveness requirement, so the 2019 and the 2022 versions have already been shown to be cost effective, and yet they are not adopted widely by the states. So 12 states are 3 or more code cycles behind the new model codes. That's over 10 years difference. And the DOE estimates that 60% of new commercial floor area is built to the 2013 version or worse. So I created this map a couple of years ago to evaluate the fixed fenestration U-factor requirements by state, just so you could see the variation. Some values may have changed a bit since then, but the story is basically still the same. As you can see, the US code requirements are not even close to requiring net zero fenestration, even in the coldest climate zones. You know, if the tippy top of Minnesota is at 0.29. So here's a comparison with the U-factor requirements in Europe using the same scale. Again, note that the European U-factors are calculated differently. So they're not directly comparable, but they aren't more than 10 to 20% different. So again, you can see the magnitude of the difference. The data indicates a much more stringent U-factor requirement in Europe, even with those differences in calculation methodologies. Even in Southern Europe, there's a more stringent requirement in some of our mild and northern states. So this shows the difference in and why we have such a difference in business as usual fenestration performance. So, but there are some areas of North America that are moving adoption of high performance fenestration faster. Highlighted here is Vancouver, BC, Boston, and Seattle. British Columbia has adopted an innovative step code that maps the path to net zero by 2030. And instead of just requiring buildings to hit an overall energy use intensity target, it also requires a specific envelope thermal performance. And this is key. And it uses a metric called thermal energy demand intensity, or what they call TEDI. This drives a focus on the envelope, not just on fenestration U-factor, but also on thermal bridge mitigation and air leakage reduction, all of which are really critical to improving building energy performance and also resilience and thermal comfort. What it does do is it prevents the large trade-offs that were happening and that happen a lot under US codes between internal HVAC and lighting systems and the envelope. So Boston and Seattle have implemented minimum envelope performance criteria in a different way. They reduce the trade-off with those internal systems when using the performance compliance path by setting a minimum area weighted U-factor called UA for the building envelope compared to the prescriptive building envelope requirements. So Seattle allows the UA, or the area weighted U factor, to be 10% worse than the prescriptive performance, while in Boston, the performance must match the prescriptive envelope UA performance, which makes it pretty challenging, especially if you want to increase your window area across higher than the baseline, which is 30% without lighting controls, or 40% with lighting controls. And that really is driving high performance fenestration in that market. What you're seeing is triple panes being used in that market, and wider thermal barriers and warm edge spacer, as we talked earlier, all the things that you would expect as you ratchet up the requirements for fenestration. As I mentioned, it's putting pressure on window area. It's also putting pressure on curtain wall performance, because spandrel performance is a lot worse than the regular opaque walls, and spandrel is treated as an opaque wall. Now, I did talk to one Boston-based developer recently, and he commented that it's changing the way that buildings are designed. It's a lot harder to do all glass buildings, but they're figuring it out. And the design community is having to rethink their designs, from changing basically having a step change from what they were considering business as usual, and they need to have new partners in their design process, including product manufacturers and installers. And his hope is that the design community will be more innovative than just reducing window area. And in fact, he shared that he's a developer, and he shared that he was able to, they had to slightly adjust the envelope for some of their new buildings that were already in the design process when the new codes came into effect, and they didn't actually have to reduce the window area very much. They were able to, just by careful considerations and some tweaks in the design, they were able to keep the general aesthetic and glazed aesthetic in their building. So some good news there. But the common denominator here are where codes are changing the landscape in terms of fenestration that's installed. The common denominator is an envelope focus. No matter which way, no matter how you approach it, the improved fenestration is only installed when you have a code that focuses on the envelope, that has basic requirements for the envelope. So installed fenestration performance is really directly related to the stringency of building energy codes and the structure of those codes. You know, do they have minimum requirements for fenestration, minimum thermal barrier size, or performance path trade-offs? It's not really directly related to the availability of technology. I love this quote from Dwayne Johnlin, who is from the city of Seattle's code office. He says, the only places you'll find high performance buildings being consistently constructed at massive scale are those places where it's the only way to get a building permit. He's also commented that to make this construction change less painful, it is important for a whole city to go through it together. If one project team decides to go it alone, perhaps aiming for LEED Platinum or Passive House, that building becomes a special order, high-risk project where everyone involved is on a steep learning curve and the supply chain is clueless, making it slow and expensive. If, on the other hand, a city announces that starting, say, 6 months from today, every project must incorporate a range of high-performance features, the landscape changes suddenly. He goes on to say, in Seattle, the energy code is our primary tool for making technical and cultural transitions to higher performance buildings. It harnesses competition in the AEC community. He commented too that entities that recently worked to defeat the new energy code are now focused on developing and promoting their technical prowess under the new rules. In fact, he's found that suppliers reduce prices as the formerly special order equipment becomes standard issue, and subcontractors work out more efficient installation techniques. And you get the economies of scale that help drive down cost and reduce perceived risk. But you know, it's not just energy code stringency that holds back adoption. There are other things too. The facade is a permanent component of a building, and this is extremely costly to remediate when things go wrong. So design teams are right to want to manage risk around the facade. So what do they say? They say things like, well, I want to use innovative products, but I need a 10-year track record, and I need it from 3 different suppliers. Also, my customer needs to see that it's first cost neutral, or at least can give me a 5-year payback. Well, then the material suppliers don't see a return on their investment because of long adoption times, and they have to wait for their competitors to catch up. And then the market doesn't see price reductions that come with manufacturing economies of scale. But if we want to drive facade performance faster, we must find alternative ways to demonstrate reliability of new products, rather than trying it out on a few small buildings and then waiting 10 years before we adopt it more widely. And of course, 10 years, as you've seen from what we talked about the last 10 minutes, you can see that in some cases, it's more than 20 years before we see widespread adoption. And in the case of many of the technologies I've shown here, you know, there's already a 20-year track record available and at least 3 equivalents, and they still aren't widely adopted. And much of the reason for this derives from the fact that the price is higher than the code baseline, because it isn't business as usual. And any delta needs to be shown to have an ROI based simplistically on energy costs. And no, not cost of carbon, not based on resilience or occupant comfort or any of the other benefits that windows bring. So what we really need to do is to create a virtuous innovation adoption cycle, one in which barriers are lowered to adoption, which then lowers product costs, which then drives further product adoption, and then also gives the incentive for manufacturers to do more innovation. And then you carry on with this continued virtuous innovation adoption cycle. But instead, we have many barriers to achieving this. I know we talked a lot about these items on the screen here. What I want to talk about now is the role of government and public policy. Public policy can help, can lower barriers, or it can be a barrier to technology adoption. But here I want to highlight several case studies in which public policy has helped drive technology adoption. So I'm going to start with the residential windows. So in 1998, windows were brought into EPA's Energy Star program, which is an above code program with above code U-factor performance. From 2001 to 2010, the market share of Energy Star windows grew from about 35% to 81%. There seem to be a couple reasons for this. One is the American Recovery and Reinvestment Act of 2009, the ARRA, which gave federal tax credits of 30% for achieving a U-factor of 0.30. This drove market penetration overnight from about 55% to above 80%. And jumps in stringency didn't affect, jumps in stringency of the Energy Star program over time didn't really affect market penetration, and that suggested that the requirements were relatively lax and didn't really stretch the manufacturers capabilities to deliver cost-effective solutions at that performance level. However, it did drive low-E adoption rates to a very high level, upwards of 98%. And one might argue that the pace of innovation was slowed by not having bigger jumps in stringency, or at least the innovation cost effectiveness balance was outpacing the standards revision cycle. But what it did deliver was a transformation in the business as usual for windows in residential homes. And what we have nothing like this for commercial fenestration or facades. I want to talk a little bit about LEDs, and there's significant market transformation happened there, and you all probably witness to this. Lighting manufacturers worked together to effectively lobby Congress. They had performance-based energy efficiency standards for lighting in governmental legislation in 2007. They had lighting standards in federal government buildings, more stringent lighting standards, I should say. They lobbied effectively for appropriations for R&D funding for solid-state lighting. They averaged $25 million a year from the federal government for R&D funding between 2007 and 2012, and received another $50 million from the ARRA in 2009, which also included funding for manufacturers to make improvements in their manufacturing processes. There isn't funding for fenestration on a line item basis for DOE. Low-E coatings, electrochromics, VIG, and R5 windows have been funded, but the amount of money put to those initiatives is relatively small compared to the financing of solid-state lighting, and of course now heat pumps, which we'll talk about in a moment. In recent years, DOE has expanded its portfolio to include R&D into manufacturing projects, largely at the direction of Congress in the 2009 ARRA funding and also the 2012 appropriations bill. What all this has done for LEDs is really transformed the lighting market. You can see that in incandescent lights is basically the market share has been decimated over the course of a decade from 2010 to 2020. And in conjunction with the reduction in incandescent lights, you can see the increase in LED lighting. The recipe for this market transformation was the industry coordination and alignment, their lobbying efforts, the willingness of the industry to obsolete their business as usual, and that's key. We don't see that in our fenestration industry. And then lastly, the legislation which directed many millions of dollars into LED R&D and manufacturing development. I want to move across the Atlantic right now to talk about the market transformation for Low-E in Europe. What we saw here in this graph, you can see the market penetration in the years before and the years after legislation was in force that required Low-E performance in fenestration. This is for Germany and the UK. And you can see the market penetration went from very little before the legislation to very high after the legislation. You can see the recipe here was 1, available technology, and 2, legislation that says you must implement this performance. So I go back to my original question. Do we need more innovation in commercial facades, or do we need to modify market conditions to adopt the innovation that we have? So the government and private enterprise have done a pretty good job of supporting innovation in fenestration, and there are certainly more opportunities for innovation in products and manufacturing, such as longer service life insulating glass units and curtain wall, high performance spandrel panels, low carbon float glass production, et cetera, et cetera. So there's always opportunity for additional R&D. But if we don't do anything about the deployment issues, more product innovation will mean more unadopted technology. So we have to change the adoption environment in order to accelerate progress. We need more focus on innovation in codes, in public policy and project delivery. Energy code structures that promote better fenestration, yet are balanced with the human well-being considerations, such that appropriate window area isn't compromised. We need incentive structures which can encourage owners and project teams to reach for higher performance, which will build capacity for specifying and installing, as well as in products, so that doing better becomes business as usual. To be effective, these incentives will need to reference above code standards with facade specific performance. And we don't have that right now. More sophisticated payback assessments are needed, and of course the associated tools to help you do that, to move away from energy costs alone to carbon, to resilience, to daylight and views, thermal and visual comfort, incorporating a more holistic view of internal systems and facade performance. Our design bid build process, which drives to the lowest cost denominator and which crushes innovation, needs to change. And ultimately, we have to rethink our processes so that we can de-risk every stage, especially at deployment. On that note, I want to just quickly mention a DOE-supported Facade Tectonics Institute project where we are identifying the barriers, all the barriers to the adoption of high-performance fenestration. We're looking at where adoption is being accelerated and why and how. And then we're identifying the levers to accelerate adoption so that we can create solutions, or what we call acceleration concepts, that can be tried out to see if we can move the market faster. Currently, heat pumps are getting all the attention. We need a better coordinated advocacy effort for net zero windows. Heat pumps are the main funding strategy for the decarbonization of buildings, but you can't get to effective decarbonization without addressing the envelope first. There just simply aren't enough heat pumps to go on the building envelope, as you can see from this picture. The strategy will fail if we don't address the envelope first, because we need to reduce the demand on the electric grid. Windows are getting very little attention and much less funding than heat pumps. And DOE's budget is less than $5 million for windows, yet heat pumps are being funded at more than 10 times that rate. The fenestration and broader facade industry needs a coordinated advocacy effort to communicate the importance of windows to achieving a decarbonized net zero built environment, to enact legislation to allocate funding for market transformation activities and state code adoption and enforcement. To do this, we need to overcome the facade community's fragmentation, our tendency to not collaborate, and lack of an existing lobbying infrastructure. And with that, I will close up. Thank you very much. If you have any questions, you can email me at helen.sanders@technoform.com. Thank you.